Thanks for the invitation to speak. So today I want to talk about some things about subregion duality and Wilson lines. This is work in progress that is almost complete with myself, Chadwin Davies. I'm going to misspell Misha's last name, but I think it's Usayuk.
Oh, well done.
And Mihoff. The only reason why I spelled his name correctly is because at one point he sent me an email listing all of the different ways that I misspelled his name. it sunk in at some point. So,
you know, I collect misspellings of Schwarzschild. I think I have at least 20 by now.
I guess we all need a hobby.
Mao is too easy. Compare with all others.
So, 21 years ago, there was a thing that revolutionized the direction of string theory when Wildenhain proposed the ADS-CFT correspondence, which is a correspondence between a boundary theory that's d-dimensional and a bulk theory that's d plus 1 dimensional. Key to the ADS-CFT correspondence was the insight that there are specific objects on the boundary theory that are dual to specific other objects in the bulk theory. And that in certain cases, instances in which those objects are difficult to compute directly on the boundary theory are relatively speaking easier to compute in the bulk theory, or at least have a different method for computing them, thus leading to the ability to do interesting consistency checks and to explore regimes that previously were relatively inaccessible. So one of these entries in the thing that is described as the Holographic Dictionary was also proposed by Wildenhain 1 year later. And it was the proposal that the expectation value of Wilson lines in the boundary theory, in the boundary CFT, is expected to be dual to the area of two-dimensional minimal surfaces in the bulk theory anchored to the Wilson line. This is a slight simplification. I can describe briefly what the simplification is. The actual proposal in 1999 is that these expectation values were not dual to the areas of two-dimensional minimal surfaces, but rather to the areas of strings of two-dimensional strings that go into the bulk. It's some minimization of that action, but one can work in a regime where this effectively snaps onto the area of two-dimensional minimal surfaces by dialing the parameters of string coupling and G Newton and the Planck scale. So this is a proposed entry in the Holographic Dictionary. There are, I think, literally thousands of tests and checks on this specific thing. In particular, it's very important in ADS QCD as a field because calculating Wilson line expectation values in QCD is a very important thing, and thus far, I believe it has been a very well-checked and strongly believed entry in the Holographic Dictionary. So now I want to fast forward 7 years to another big shock in our community, which is the discovery of the Ryutake-Yanagi formula. So the Ryutake-Yanagi formula says that if I have a boundary theory and if I have some subregion of it, like this, the entanglement entropy of it, the entanglement entropy of this region A is given by the area of the minimal surface in the bulk subtending it over 4G. So note that this area is a codimension 2 area. So it's the area of a codimension 2 minimal surface going into the bulk. Good. So this is a thing that people proposed, and this motivated in particular, people to start thinking about the interior of this object. What I mean by that, the interior of that object is the region of space-time which is bounded by the Ryutake-Yanagi, or later the time-dependent generalization, the HRT surface, and the boundary theory itself. So in this case, it would be this region. For a slightly less trivial boundary topology, it would be either this region or this region, depending on which minimal surface was smaller. So there can be phase transitions in the shape of the entanglement of this object. This object is called the entanglement wedge. So in more papers than I can remember, but in particular I'll mention a few. The JLMS paper about the equivalence of bulk and boundary relative entropy, and the bulk reconstruction papers, of which there was one that was done by the Stanford group, by Patrick, Brian, Michael Walter, I'm sure I'm forgetting people, and another one that was done by the UIUC group led by Faulkner, to basically reconstruct the operators that are defined to live within the entanglement wedge. So this family of things led to the term subregion duality. Which effectively is the statement, there's a forward direction and a reverse direction for subregion duality because it's supposed to be a dual statement. The forward direction is, given access to the operators in the boundary theory in the restricted subregion A that I have access to, I can use that information to reconstruct operators within the entanglement wedge, given only knowledge of the reduced density matrix of the boundary state. And indeed, this has been shown well in the various bulk reconstruction papers. The reverse direction, however, must also be true in order for it to be a duality. And the reverse direction would be the statement that if I wish to reconstruct operators in the boundary reduced density matrix A, in that subregion, that somehow knowledge of only the operators inside the entanglement wedge should be sufficient to perform that reconstruction. Okay, so now I want to talk about something a little bit more recent from earlier this year. In a paper with myself, Charles, Fischetti, C. I really should ask my collaborators to exclusively end their last names with AO, make things easier. And Cindy Keeler. We proved the following theorem. So we proved that, so consider a boundary region in a CFT with disk topology. So what does that mean? It's easy enough to draw, but it's good to have a picture of it. You take a CFT, you take a disk region of it. Right? So for this region, if one is given all areas of two surfaces that are minimal, or extremal if you want the time-dependent case, anchored to the interior of A, then this allows you for a unique reconstruction of the metric in the region foliated by these two surfaces. For space-time dimension greater than or equal. So this is the theorem that we were able to prove. It required talking to lots of mathematicians, or more precisely, Charles talking to a specific mathematician many times because he refused to talk to the rest of us. But using those results from the fields of boundary rigidity and slight generalizations of those, and allowing for the fact that when we work in ADS-CFT, we allow ourselves a little bit more freedom than the mathematicians allow themselves when they're thinking about the kinds of manifolds that they consider. Sorry, a little bit less freedom. We're able to prove this theorem. So this theorem tells us, let me just draw it pictorially. If I have a boundary region like this, A, and I consider the locus of points that are reachable by two surfaces. Sorry for drawing geodesics, but my drawing skill is bad. In the bulk, the space-time region that I can reach with those two surfaces, if I'm given this data, I can reconstruct a metric in that region. So what does this have to do with everything else that I've said so far?
This is for any state?
This is for a state with a semi-classical bulk.
But it could be like a black hole or whatever. Like,
That's right. The way that black holes and those things will enter into obstructions here is that the black holes will give you regions where you don't have a foliation. So you can push up to the point where you retain the ability to have a foliation. But if there's a region that you cannot have a foliation with these two surfaces, then you can't reconstruct the metric in those regions. So in that way, you still can't reconstruct the shadow regions.
One more, this is a really dumb question, but this theorem doesn't seem to have anything to do with the CFT actually. It's just a statement about minimal areas in a like Riemann surface, or?
Yes.
Yes, okay.
Yes. That's a very good point.
but
Are there, yeah, go ahead.
you're sort of, it's a theorem about space-time or about space?
It's a theorem about space-time. So this reconstruction works covariantly.
I see.
And you mean disk, not the ball shape region? Disk and the two surface?
Yeah, it can be an ellipse. Like the boundary region doesn't have to be spherical.
Oh, no, I mean dimension. It's a topologically ball shape region or really ball shape region, I otherwise mentioned it.
Yeah, ball shape region.
Ball shape region, right?
Yeah.
So then two surface means, of course, co-dimension two surface, right?
Depending on the space-time dimension.
It's always an HRT surface.
No. That's what I'm going to.
So this is a purely geometrical theorem.
Yes, that's
It is
that's a very good point, which I'm about to address.
okay. That it is the asymptotic ADS an assumption or no?
Yeah, you need the space-time to be asymptotically.
For this to hold.
Yeah, I think there are generalizations actually away from the situation where the space-time is asymptotically ADS. Mathematicians in general don't care at all if the space-time is asymptotically ADS, and so this is a property of Riemannian manifolds. So like Charles was saying, amusingly, this field of study was, there are two kinds of people that work on this. There's like pure mathematicians that work on differential geometry, and then there's like people that work in medicine and people that work in geology, because this is also exactly what you would do to probe the structure of the Earth. Or if you want to take an X-ray of someone, you're taking a bunch of beams that shoot at a thing and you're trying to reconstruct the shape of the thing that it's shooting at. So you get two very different kinds of papers when you read in this field. One with one that's very general and one that's very not general.
But in the second time, there's no ADS.
Sorry, again, is it static?
No, it's not static.
That's not static.
Not static. So I'll just write covariant up here. And you can look at it if you think it's static.
And still you say that if one is given all the areas in two surfaces?
Yeah.
Two surfaces.
Two surfaces. So
Good. So that means it's
Codimension.
yeah, two surfaces.
no
Two
no,
surfaces,
Yeah,
sorry.
yeah,
Two-
that's
it
why
really means two. Okay, okay, okay,
That's
okay.
why. So it's like something like a string, really, like
Yes.
in a ball.
That's
So
right.
you have to have like a point particle, 2-point particle, and the ball. Whatever.
Right.
You probably go there. But,
It's mysteriously and suggestively similar to this portion.
yeah, yes.
Which I'm about to talk about.
Yes.
Okay, so as people have asked me, as 3 different people have asked me now, indeed, I'm talking about 2 surfaces in general and not always HRT surfaces. So when D equals 4, then people are totally happy because then the dimension 2 surfaces are equal to the codimension 2 surfaces. And so this is just a statement that you can reconstruct the metric with access to all of the HRT surfaces that are anchored to the interior of the region that you have. So this fits nicely with our intuition and is great. But the theorem explicitly works for D greater than or equal to 4. So in particular, this works for D equals 5, where these dimension 2 surfaces are going to be different from the codimension 2 surfaces, which are dimension 3. So already, this is an interesting situation because now there's a difference in terms of how deep into the bulk one can probe with these dimension 2 surfaces versus the codimension 2 surfaces that you had before. Now, one reason why this might be, one reason why you might have thought that this would be uninteresting is also something that people say, which is, wait, isn't this just a fact about geometry? If it's just a fact about geometry, then maybe it has nothing to do with ADS-CFT, because maybe these dimension 2 surface areas that I'm talking about don't have a nice boundary interpretation. Indeed, one of the possible nice boundary interpretations I just explicitly ruled out for higher dimensions, that being the entanglement entropy. So now, this is when I want to draw your attention back to this claim of the holographic, of a proposed entry in the Holographic Dictionary from 20 years ago.
Is it known not to work for other dimensions? Like, you shoot lines or you do that actually have HRT surfaces?
So we're working on trying to explore whether or not we can generalize this proof to different dimensional surfaces.
But there's no counterexample.
There's no counterexample that I know of. I know that the specific proof technique that we use is based on, so just to say something technical for a moment, it's based on Dirichlet-Neumann maps that are very specialized to 2-dimensional surfaces. And so if you want to use geodesics, you would have to change the proof technique for that reason. If you want to use higher dimensional surfaces, then without going into details, it turns out that an equation that you need to be exactly constrained becomes under constrained. And so if you use this proof technique, so you need to use a different proof technique that gets around that apparent constraint.
I'm not completely agree, or at least probably not swallowing your statement that if it's a completely geometry, it's not interesting at all. I don't think, because if it's a completely geometry,
I'm not making that statement.
oh, okay, but I'm saying, yes,
I was making a straw man statement such that if someone felt that way, then I could address his feelings.
okay, yeah, let me just say, I mean, if that's the case, then somehow geometry, theorem of geometry knows something special about the one-dimensional object in a bulk, namely string, right? So it's regardless of asymptotic ADS boundary.
Sure.
So that's pretty interesting.
Yeah, I agree. But I think that because of this earlier proposed entry in the dictionary, we may be able to say something stronger. So, what do I mean by that? Well, in some sense, it's kind of immediate. The expectation value of Wilson lines of a boundary subregion is data that one should be able to reconstruct from the reduced density matrix of that boundary subregion. I don't think that's a controversial statement. If you try to act outside of the reduced density matrix with any sort of unitary process, you're not going to affect the Wilson line expectation value inside that region. So if this entry in the Holographic Dictionary is correct, then what it means is we indeed do have a useful boundary information theoretic object. Well, maybe not, maybe information theoretic is the wrong word. A boundary CFT object that calculates for you these areas that you need to reconstruct the metric. Indeed, one could have gone one dimension lower and talked about dimension 1 objects as well. Talked about geodesics. There we have the geodesic approximation where for a large class of spacetimes, we believe that the 2-point function of boundary regions, of 2 points in the boundary is calculated roughly by the geodesic separation of the bulk of those 2 things based on some saddle point approximation. Now again, the reason why we're not focusing on that case here is because our proof technique is specialized to 2 surfaces. And so that's why we're not focusing on that case. There are also potential issues with analyticity in that situation that I'm not going to talk about for now, but I'll come back to later. So it actually ends up being the case that you can show that if I pick the correct shape of the boundary region, even if it has a disk topology in 5 dimensions, so I'm going to try to draw a 3+1 dimensional boundary region. It turns out that if you draw a region that's essentially a pancake, so it's like it's an ellipsoid where 2 of the semi-major axes are much, much longer than the remaining semi-minor axis, then you can intuitively see that the area swept out by these dimension 2 surfaces will probe much, much deeper into the bulk than the regions probed out by the HRT surfaces. And you can argue this kind of by using entanglement wedge nesting. The way that you argue this using entanglement wedge nesting is if I consider this squashed pancake, then I can consider the circumscribing sphere and the inscribed sphere of this object. And I can argue by entanglement wedge nesting that the entanglement wedge of this squashed sphere will be contained within the entanglement wedge of the circumscribing sphere and will contain the entanglement wedge of the inscribed sphere. And what's more, by symmetry arguments, you can actually show that for dimension 2 objects that are anchored to things on one of these spheres, they will always lie on the surface of the sphere. So you know that the dimension 2 objects that kind of go along the long directions penetrate kind of very deeply into the bulk, and the dimension 2 objects that go in the short direction kind of penetrate very shallowly into the bulk. Now, because we know that it's also possible to argue that the entanglement wedge of the squashed ellipsoid that you're considering is in some sense the geometric mean of the entanglement wedges between the inscribing and circumscribing spheres. And so it's going to shoot some difference here when you construct this entanglement wedge. And so based on that intuitive picture, these 2 surfaces that go along the long direction will go very far outside of the entanglement wedge. Moreover, it's not a perturbative effect, meaning that if I take these endpoints and I move them slightly inside, then all it's going to do is move this inwards slightly. It's not going to non-perturbatively force it to be inside the entanglement wedge. This is a hand-wavy intuitive argument, but we can prove this in general. So we can prove that for disk-like regions, if you pick the correct boundary disk-shaped region, not only do these dimension 2 surfaces generically probe outside of the entanglement wedge, generically these dimension 2 surfaces, the locus of points that they contain in a fully foliating region will contain the entanglement. Will strictly contain the entanglement wedge. So now I want to, what does this have to do with the thing that I erased before, subregion duality? Well, now I'm a little bit confused if I'm talking about strict subregion duality. Why am I confused? The reason why I'm confused is because now it seems like the boundary data allows me to learn more information about the bulk spacetime than just information inside the entanglement wedge. Now, I'm not making a claim that the entanglement wedge is unimportant or that it's not distinct. In particular, I am not making the claim that in this larger region I can reconstruct every operator in this region, like I can in the entanglement wedge using the bulk reconstruction argument that Patrick's group has made. What I am saying is that there is some data about this region outside that is somehow encoded inside the boundary subregion. And moreover, I want to argue that the data that is encoded in the boundary subregion is not secretly encoded inside some fluctuations of operators inside the entanglement wedge. So in particular, I want to consider, for example, 2 different spacetimes. I'm going to draw these in lower dimensions just so I can draw them, but I actually mean these in ADS5, asymptotically ADS5. I can consider 2 different situations where I fix by hand that the entanglement wedges of the 2 regions are exactly the same as each other. And I can consider situations where the geometric completions thereof are different. How can I do this? Well, I can exploit something like Birkhoff's theorem in GR and have, for example, in one thing, some black hole there, and in another thing, like a spherical ball of dust like this that has the exact same mass as the black hole, is spherically symmetric in exactly the same way, and is sufficiently far away from the entanglement wedge that you don't have to worry about stray entanglement between something inside the entanglement wedge and something slightly outside. Now, because we can engineer these 2 surfaces based on the boundary shape, independent of the form of the geometry, to probe arbitrarily far outside of the entanglement wedge, barring a topological obstruction, we can come up with situations where it looks like this, where one of the two surfaces goes like this and it wraps the black hole, but here there's no topological obstruction, so here it can go like this, and go inside. And in those situations, we can have situations where the area of this surface and this surface are markedly different from each other.
I mean, doesn't it already follow from your theorem that you're going to be able to distinguish the metric in these two regions?
Yes. I'm just
clearly
making,
distinguish between these two cases.
I'm just making maybe an unnecessarily pedantic point, but yes, that's true. Right. So this is a little bit troubling because this tells me that I can have a situation in which I can enforce the density matrices of the entanglement wedges to be exactly the same, but the boundary data on the that the entanglement wedge regions are homologous to do not have to be the same. So you might immediately worry about how this could possibly be consistent with some of the letters that I was writing earlier.
Is it just an order counting thing? What you're reconstructing here is like classical data at order 1 by g, whereas all these other letters are all about effective theory at order 1. So what you're reconstructing isn't like, aren't quantum operators in the effective theory, right? They're just like some classical facts about the coherent state in the boundary.
Yeah, I think so.
Right.
Right. So that was one of the, well, okay, that's I think related to the next thing that I'm going to say, but you can tell me if you disagree with what I'm about to say. So you might be a little bit worried about how this could possibly work with JLMS and Don Harlow Wall, because someone would say, well, okay, JLMS tells you that the relative entropy between two reduced density matrices in the bulk and the relative entropy between their corresponding boundary subregions are equal to each other. And so if they're supposed to be exactly equal to each other, how can it be that this relative entropy is clearly 0 and this other relative entropy is clearly not 0? It's in fact easy to see that it's clearly not 0 because these two are different space-time geometries, and in some sense they're relatively close to orthogonal to each other, not exactly orthogonal. So the relative entropy between the two of them should be large, because in some sense, if you like, the areas of these two surfaces define a kind of a thought basis for holographic spacetimes for you.
So when you say relative entropy, you mean between which two states?
Good. So let me call this rho prime and sigma. So that's what I mean.
I mean, the reduce does that match?
The reducing to me.
At the box. But you were using boundary relative entropy equals positive relative entropy, right?
Yeah.
In the box there are no quantum states here that you could.
Right. So I'm going to say why that's a little bit too quick. So for both of these papers, the thing that one needs to do is this, but this is not some curse word. One actually just needs to read the fine print when it comes to both of these things. Right. So JLMS is a statement that's true perturbatively. So JLMS is a statement that you can prove is perturbatively true when rho and sigma have relatively small relative entropy compared to each other. This is why when Guri and friends do these quasi-local energy calculations based on JLMS, they consider the vacuum state or some specific space-time in a very small deformation away from it, such that they can control the size of the relative entropy. In this situation, because I can think about these areas as putting you in different thought states, there's nothing requiring the relative entropy between the boundary states needs to be small, even if the relative entropy between the bulk reduced density matrices is exactly 0. So, in some sense, we can reconcile with the issue with the naive issue that one might think holds in JLMS. Now, with Don Harlow Wall, it's exactly the same thing. The issue that might trouble you is the notion of complementary error correction. That, in some sense, if I have access to this data, why doesn't this ruin the complementary error correction statement? They have some theorem whose exact form escapes me at the moment, but it's the one that it talks about. But the fine print there that's relevant is that there it's relevant that the two bulk spacetimes that they're considering are in the same code subspace. So it's just the quantum error correction version of the same perturbative statement that people were making in JLMS. And I think that one can argue that I can certainly consider two different geometries for which the reduced density matrices inside the entanglement wedge are exactly the same, but are not in the same code subspace. And so in that situation, this is in no sense a small perturbation on this. And so there's no argument that complementary error correction should get you out of this separation.
Are you saying that the notion of the code subspace from the boundary point of view is about the local operator? Or no?
I'm not
If
sure.
you think about Wilson line and so on, that is sensitive to something beyond. If you have access to A,
Yeah.
the code subspace is only a set of states, not the whole state.
Yeah.
But Wilson line in this A, region A, has
saying that-
access to the different.
You're saying that Wilson lines are naturally non-local operators.
And then it goes outside, the probing outside of it.
Right.
It's almost like that.
So I think that's equivalent.
But counterposing to that is that the notion of the code subspace is about the local operator only.
I'm pretty puzzled. So like in the right case, the little picture you drew,
Yeah.
I could take the metric somewhere outside the entanglement wedge of the thing in the lower right corner. And according to the usual story, that's reproducible in the other part. But now according to your here and here, I can also learn it from that part. So it looks like I'm getting the same operator in two different places.
I think
It's not an operator.
it's not an operator.
It's a classical object.
Like it's a question of whether or not it is correct to view the metric expectation value as an operator. I think
Well,
Rob-
no, that's obviously not right, but I mean, but you okay, I mean, okay, fine.
I mean, if you find a sharper version of it that is a problem, definitely tell me because I'm very concerned. So
Just two comments. One is like there's a very much more obvious example of this, which is like a collapsing black hole. Where after the page time when the extremal surface jumps to just behind the event horizon, you still know the metric behind the black hole because you collapsed it from a non-black hole state, right? So you all this another example which, in hindsight, is like a simple example.
yeah, I'm sure that there are other examples.
Yeah.
In this case, I just really wanted to focus on a case in which the geometries were as, if you like, vanilla as possible, so that people don't yell at me about the information.
Yeah.
All right, in that case, do you really know that's been, aren't you assuming you didn't act with something crazy on the radiation?
Sure, but like.
But he's not assuming that here, he just has
No.
the state, right?
Fair. Simpler in the sense of like people here already know. It's not simpler in the actual calculations, as I guess. Yeah. Fair.
No, sorry, I don't want to harp on this, but it sounds like they're physically different situations. There you're assuming someone did not do something to some other state. Here he's saying, just given this, you know for sure what's beyond.
Fair.
Regardless of what they did to that other
Yeah.
part.
I think it teaches us that, you know, we have to be careful about the sort of colloquial use of reconstructing some region. And I think the sharp statements are all in terms of operator, error correction, and so on.
Yeah.
And they really do refer to quantum mechanical operators in some code subspace and so on. And the metric is just not part of that.
You have a situation where you can consider two Wilson lines and then the surface will connect them.
Yeah, so the thing that runs into is this thing. We believe we have a way to generalize away from this. We think that the word arguments work out, but we need to convert the word arguments into math arguments. And so like we think that we can talk about situations where A is a disjoint set of two things, and then we can do the calculation that you're suggesting. And we believe that the same sort of thing happens there. Right. So it seems here that there's a tension that we're being confronted with between two things. The first thing is this entry in the Holographic Dictionary, if it's correct. And the second thing is what I like to think of as the folklore version of subregion duality. So the proven version of subregion duality is in terms of as Raphael said, is in terms of code subspaces, operator algebras, all of the things that are proven. I'm not saying there's anything wrong with JLMS or with Dom-Harlow-Wall as proven. The colloquial version is, in some sense, the boundary reduced density matrix of that region is in some sense the same as the bulk reduced density matrix of the entanglement. And that seems to be the tension that the thing that we're finding is in tension with this statement. Now, I want to present all sides of this argument to make sure that I'm not like playing too fast and loose with this. So certainly, one could weaken the subregion duality claims just to things that are proven to be correct, and that would resolve this tension. Another way that you could resolve this tension is if this entry in the holographic dictionary is not correct, or is only true for a restricted subset of things. So,
sorry, I don't quite.
Yeah.
So why can't I just say that operator is outside the code subspace?
no, you can't.
Yeah,
I'm just saying that some people, that this is one of those things where there's a potential for people to think that subregion duality, as proven, is a stronger statement than it actually is.
But it's proven for the code subspace.
Yeah.
That's right. I'm just saying that some people might inadvertently try to use it outside the code subspace.
I mean, like, you kind of expect that code subspace has something to do with bulk effective theory. You can calculate this Wilson loop in bulk effective theory. That is the point, right? So,
with linear boundary theory. With linear boundary theory, you can discriminate which code subspace you're in, and all code subspaces has isomorphic structure regarding local operator or subregion duality.
That's probably, what you said is probably true. I would need to think a little bit more about it.
But yeah.
But yeah. Right, so the other possibility is that this entry in the holographic dictionary is not correct for all spacetimes. And this is when I want to go back to the statement that I was making about geodesics that people were asking about earlier. So in the year 2000, Morel, Foucault, and Ross wrote a paper where they showed that the geodesic approximation isn't always right. That in particular, if they consider a time-like geodesic, a time-like two-point function in a black hole background, they can show that they can do the geodesic calculation, because that's just a simple GR calculation, and they can do the time-like calculation on the boundary because it's a specifically symmetric thermal situation, and they find that they don't match. And so, as far as I know, the examples that I know where the geodesic approximation doesn't work are situations like that, where you have time-like geodesics in some kind of complicated background. So you can prove the geodesic approximation always works if your space-time is analytic, and you can further prove that the geodesic approximation doesn't work in these specific cases. So now there are two possible stances that you can take, depending on if you are like really a GR person or more of a CFT person. The really GR stance is that the geodesic approximation is only true for analytic spacetimes, and that if you insert any bulk matter into your thing that doesn't have support everywhere, the geodesic approximation doesn't hold. If that's the case, and a similar thing held here, then there would also be no tension, because the fact that the analytic, that it only works for analytic spacetimes means that I can exploit the properties of analytic functions to say that if I know the metric in any small region, in particular inside the entanglement wedge, then I can use that to say that I know the metric everywhere. And so then the ability to push outside the entanglement wedge with metric reconstruction in particular would not be a surprising statement. However, that's a little bit, that bothers me because that kind of trivializes the geodesic approximation. It says that like, I can put balls of dust, whatever, these things that we normally think are totally fine to consider in GR, and we can consider them in relatively sedate situations where there's no time dependence, where we're thinking about a static case. In this case, we can think about a static case, and it's not specifically covariant in this case, but we can take a static case as a specific example. And we expect that something like the geodesic approximation should still be true, because people calculate it in the boundary field theory and they get matching answers for elements, in particular inside a thermal ensemble instead of the exact thermal state. And those are exactly non-analytic inside the horizon region. So because of that, you might expect that the Wilson line expectation value thing, because it's in some sense a generalization of the geodesic approximation, should also be true for non-analytic spacetimes. So that's a potential issue with resolving the tension in that way. There's another argument that geodesics in particular might be bad because you can imagine using the extrapolate dictionary to compute a two-point function of two bulk points that are both inside the entanglement wedge. Certainly I can calculate that from the entanglement wedge reduced density matrix. And then you can make the same arguments as these things by just continuing those points to the boundary. And then you can ask, well, what went wrong? How does the entanglement wedge know about geodesics that go like this? So the way around that fact for Wilson lines, that is indeed, I believe, a problem for geodesics. The way around that for Wilson lines is that, as far as I know, there is no equivalent of the extrapolate dictionary for Wilson lines. Like, there is no sense in which a bulk Wilson line is equivalent to a boundary Wilson line under the extrapolate dictionary. And so because of that, you don't have that safe harbor to appeal to in trying to reconcile these two things. So my view of this work is that basically what we're doing is we're using a result that Charles and I proved for geometry. We're marrying it to a result that Juan argued existed for all holographic, as an entry in the Holographic Dictionary. And we're showing that together they seem inconsistent with the strong form of subregion duality that some people could assume follows from the weak version of subregion duality that is thus far proved. My watch is dead.
So, can I ask, see if I understand? So, you're saying a way to think about getting around this, if I understand correctly, is that the general answer is you compute the path integral of the bulk with this string world sheet inserted and it fluctuates and blah, blah, blah. But the approximation that it's equal to E the minus tension times area of some minimal two-surface could fail unless the geometry is a very special, like, analytic, or maybe without the scare quotes, analytic type. Because otherwise it seems like you could just act as something crazy on a complement and totally screw up the geometry. And by construction you wouldn't know that in the other part.
Sure.
So is that what you're saying a possible way out of this tension is?
Yes, but I believe that if you act with something extremely crazy on the outside, then you might also ruin the ability for the for a foliation to exist deep in the entanglement. Right? Like if I just basically turn everything outside of the entanglement wedge into a giant swirling black hole or something, then then these foliations would also be prevented from probing far outside of the entanglement wedge by the new
I
entanglement
don't
shadow.
understand, because as Brian argues, it can't affect the expectation value of the Wilson lines. I thought all you need to know is all the areas, which is the same thing.
Yeah, I think it can't change the Wilson expectation values, but it would just no longer be the case that that expectation value is equal to the geometry of some minimal surface.
Right.
Yeah.
I think that
I see.
Yeah.
I think that's like a way out.
Yeah.
If someone wanted to make an argument like you mentioned, where you actually analytically continue the actually analytic metric, you might run into the issue that analytic continuations fluctuate wildly with respect to changing the values in the patch that you're continuing from. So it might require a precision of the metric on that patch that's inconsistent with the blurriness due to the gravitational covariance state.
Right. So can I try to rephrase what you said to see if I understand?
Yeah, sure.
So you're saying that gravity is in some sense fundamentally non-linear, that there's some fundamental smearing of gravitational degrees of freedom.
I wasn't commenting on that per se, just that the coherent state of the metric would not have a definite value of the metric.
Yeah, I think I agree with that. I think it might be related to what I said, but separately I guess. Okay. Does anyone know what time it is? I watched that.
4:60.
Okay. I guess there's any other something else I wanted to say. There was, but because I'm old, I forgot.